Now we are talking about some additional aspects about the hybridization, because about hybridization, the various aspects we already covered. Now you can say hybridization part 3 we are going to study today. Till now, what we have studied, let us revise. sp hybridization, example is BeCl2. If I consider the sp2 hybridization, yes, what's the example for sp2 hybridization?
BCl3.
Yes, BCl3. For sp3 hybridization, example is SiCl4. The format of explanation are given, point wise explanation given. Similar approach you have to apply for this all hybridization that I covered in the hybridization part 1. Afterwards, I discuss 5 coordinated or 5 bonded compound. What is the example of that? PCl5. Yes, what is the type of hybridization?
sp3d.
sp3d. Yes, brilliant. After that, sp3d2 also you can study. That was a homework given to you, and that can be or the SF6. Similarly, sp3d3 also you will understand, that we have discussed in the part 2. Now today we are discussing some additional aspect of hybridization. What you know so far, sp3 hybridization means it is a mixing and recasting and redistribution for s and p orbitals. How many p orbitals are there in sp3? 3. And how many s orbital? 1. Total, if you see, total number of orbitals are 4. I want to know from you, what is the percentage of s character? How much percentage of s character is there? I want to know from you, how much percentage of p character is there?
50%.
I could not hear you clearly, Shubham. S character how much?
50%.
No. See here, total 4 orbitals are there.
25.
Yes. S character is 1 among those 4. So it is 25%. S character is 25% in sp3 orbital I am talking about. See, S was a 1 orbital. Px, Py, Pz, those were the separate orbitals. Now I am talking about new, modified, modern, hybrid orbital. That's a sp3 orbital. In that sp3 orbital, how much character of S is there? It is only 25%. And how much character of P is there? It is 75%. So we expect that whatever the 4 sp3 orbitals are there, I represent those all 4 sp3 hybrid orbitals. See here, you consider it as a 1 sp3 hybrid orbital. You can consider it as a second, third one. Similarly, the 4th orbital also you can what consider here. Yeah, likewise, the 4th one. Let me label those orbitals. Let me consider it is a first sp3 hybrid orbital, second one, third one, 4th one. Actually, it is only 1 orbital, but lobes I am saying. First lobe, second lobe, third lobe, 4th lobe. As per our current understanding, what we say in that first orbital, S character is 0.25, or as Prathamesh said, it can be 25%. It is a 1 orbital. When we come to the second orbital, same conclusion. S character will be 25%. About third orbital, S character is 25%. About the 4th orbital, S character is 25%. Similarly, I hope you will understand if I say in that first orbital, the P character is 75% or 0.75. In the second orbital or second lobe, the P character is 75%. Here also P character is 75%. P character is 75%. It is the ideal situation when all orbitals are equivalent, or orientation is equivalent, or the atoms surrounding are equivalent. Means if I consider SiCl4 or as you say CH4, these are the uniform conditions. About that I have no question. But this ideality may not be there for every molecule, there will be the few molecules where this ideal situation will not be there. Practically, the different percentage for S and P character will be there. Different S and P character will be there. For example, if I consider ammonia molecule where one lone pair is there, or second example, if I have to consider, just wait, somebody wants to enter, Ganesh. Water molecule OH2 where two lone pairs are there on oxygen. Okay, forget about these such molecules where lone pairs are there. Simple, if I consider a carbon, two fluorines and two chlorines. If CCl4 would have been there, it is uniform. All atoms are same. But if CF2Cl2 is there, then it is not uniform. Yes, students, are you following what I'm saying? No, I'm not understanding. Are you following or not? If no, then say no, I'll repeat.
Repeat, sir.
Okay, fine.
Repeat, sir.
Yeah. Okay. Thank you. Yes, you'd respond. And don't allow me to ask again. You have to say directly no. I will be happy to know your responses. See what I'm saying? Usually, when we consider any orbital, say sp3 orbital, we say that there will be the 25% of S character and 75% of P character. In any lobe, this lobe also same situation, second lobe also same situation, third lobe also same situation, fourth lobe also same situation. These situations are there where in case of CCl4, in case of SiCl4, in case of CH4, where all atoms are same. This is an ideal situation, but it will not be always. Situation is different. When we consider a lone pair, means out of these four orbitals, 1, 2, 3 and 4, out of these four lobes, one lobe will be with lone pair in case of ammonia, and other three lobes will be with bond pair, where in case of ammonia. Similar approach. Total there are the four lobes, first, second, third and fourth. If I have to talk about the water molecule, see here, OH2 molecule, two lone pairs are there. So out of those four, two lobes will be with lone pair and remaining two orbitals or lobes will be with bond pair. This is the case in case of water. Here uniformity is not there. Equivalent orbital concept is not there. So different contribution for S and P is there than our expected condition, than our expected contribution. It is also called as non-equivalent nature of orbital. Orientation is a task. By the way, which atoms are there, which kinds of orbitals are there, whether they are the bond pairs or lone pairs, that differs the orbital, that differs the equivalentness. In case of this SiCl4, CCl4 or CH4, there is equivalent nature. Equivalent orbitals are there. But here, non-equivalent orbitals are there. Additional example I had given to you, this one, where two fluorines are there and two chlorines are there. So out of those four orbitals, two orbitals will form bond with the two fluorine and two lobes will form the bond with the two chlorine. And every lobe will be with the different nature, different S and P character. That's a difference in the S and P character than ideal situation is possible, that I am saying. Is this point clear now?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir. Yes, sir.
Okay. Go on replying fastly so that we can move next. Now I talk about the sp3 hybridization only. Example is ammonia molecule. First, let me discuss. What's the formula of ammonia?
NH3.
Yes, NH3. And this NH3 has one lone pair. If I have to explain the hybridization as per our usual pattern, first I will consider this molecule and we will consider the central atom, and that central atom is nitrogen. Atomic number is 7. Its electronic configuration, if I have to represent, then helium, that's a previous noble gas, 2 electrons are there, that's a 1s2. Afterwards 2s2 and 2p3 likewise we can represent. If I have to represent it in terms of the block diagram, then the 2s orbital will be with 2 electrons, that's a pair of electrons, and 2p orbitals 1, 2, 3 electrons. Each orbital, say px, py and pz will be with unpaired electron. So we were expecting that this nitrogen in ammonia will form 3 bonds because 3 unpaired electrons are there. But nitrogen undergoes some change, and to have that change, energy is needed, and that change is called as, yes, help me, what is that change? What is that change that nitrogen undergoes, then bonding occurs?
Hybridization.
Yes, hybridization. Which hybridization? Which hybridization that nitrogen will undergo?
sp2.
No.
sp3.
Yes, sp3 hybridization. Actually, nitrogen needs 3 unpaired electrons, and those 3 unpaired electrons are already there. There is no need of hybridization by general point because 3 hydrogens are there, 3 bonds it has to form, but nitrogen does not do that way. Nitrogen invests time in hybridization. Nitrogen invests energy in hybridization. Nitrogen carries the burden of that lone pair. If only these 3 orbitals, if I consider, then what would have been the bond angle? Px, Py, Pz. What is the angle between those orbitals? Between Px and Py, or Py and Pz, or Px and Pz, how much angle remains? Angle between those orbitals? No, can't hear. Help me. Yes, between the x and y and z, how much angle remain? That's my simple question. What is the angle between x-axis, y-axis and z-axis?
90 degree.
Yes, why are you dealing? I'm not understanding whether you don't want to answer intentionally or you're testing me. That I'm not understanding. Yes, the bond angle was expected to be 90 degree, where in case of the ammonia molecule. But what is the reality? It is not. Bond angle is not 90 degree. What is the reality? How much bond angle is there? That bond angle is, in true sense, it is 107 degree. It is not exactly 109 degree 28 minutes also. So it is 107 degree is the angle somewhat near to the sp3 hybridization. Therefore, we are considering here is sp3 hybridization. We have to answer here why it is not exactly the 108. What is expected number for sp3 hybridization? It is expected that the angle should be 109 degree 28 minutes. It is expected, but this expected bond angle is not found. Which angle is found? Angle was found as 107 degree. The difference is due to difference in S and P character is one of the reason. Let us discuss by simple way. What I said to you, if that nitrogen would have not been undergoing hybridization, then angle should be 90 degree, which is not the reality. So certainly nitrogen is undergoing one change, and that change is none other than hybridization. Which hybridization? sp3 hybridization. So what we need to understand, the nitrogen undergoes this sp3 hybridization. This s orbital and these 3 orbitals, they will overlap, they will mix, they will recast, they will distribute the energy, and there will be the sp3 hybridization. Who undergoes that sp3 hybridization? Nitrogen undergoes the sp3 hybridization. And that sp3 hybrid orbitals, if I have to represent, see here, it's a 1 lobe, 2nd lobe, 3rd lobe, and 4th lobe. 4th lobe for the nitrogen you are considering. Out of this 4 lobe, 1 lobe will be with lone pair. 2 electrons will be there. Remaining lobes are with only 1 electron. And these lobes, it is which orbital? It's a sp3 hybrid orbital. Of course, there will be the antinodal points. Means here will be the small portion, here 2, 3, and 4. 4 small portion will be there. If positive station we consider, positive phase for the orbit we consider, negative phase also will be there. And this sp3 hybrid orbital will overlap with orbitals of the hydrogen. Here see, it's a spherical in nature. It's orbital of hydrogen, orbital of hydrogen, orbital of hydrogen. And hydrogen remains with which electron? 1 electron in 1s orbital. 1 electron in 1s orbital of hydrogen. So they will overlap. Due to which I can represent the structure for ammonia as nitrogen electron. I can represent here bond pair, first bond pair, second bond pair, and third bond pair. It is bond pair, first bond pair, second, and bond pair third. And upside is a lone pair. What till now we discussed with you, because of the existence of this lone pair. Because of this lone pair is bulgier because of its large size or large space it occupies and more focus, more concentrated it is. What will it do? It will repel these bond pairs. This bond pair, repulsion will be there. This bond pair will repulsion, due to which bond angle remains less than usual expected bond angle. That's a 109 degree 28 minutes. And exactly how much it is, that bond angle is here. Which bond angle? H and H bond angle. This bond angle. All you can consider. First, second, third, and similarly from this third bond and this first bond, if you consider, there also you will find the same bond angle. And what is that bond angle? 107 degree. It is because lone pair repels strongly bond pairs, and because of that they got shrink, they got compressed, and therefore that bond angle decreases. That remains our general understanding for explanation of bond angle in ammonia. Students, could you able to understand what I'm saying?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
Yes. Go on answering. Very good, very good. Now I'm informing the modern approach. I said already, if there remain a sp3 hybrid orbital, 2, 3, that's the third orbital, and the fourth orbital, what we consider, every orbital is with same S and P character. We consider S character as 0.25 or 25% and P character as 75%. Now we have to think logically. Expected bond angle was 109 degree 28 minutes. It is because of what? Because of sp3 hybridization. But observed bond angle, how much? It is 107 degree. Which orbitals are there? S orbital and P orbitals are there. How many P orbitals are there? 3 P orbitals are there. What is the angle between the Px and Py orbital, or Py and Pz, Px and Pz? How much angle? Generally, I'm not talking about hybridization now. Generally, in Px and Py orbital, how much angle remains? Py and Pz orbital, how much angle remains?
90 degree.
Yes, it is 90 degree. So now, what logic you will apply? You are with 3 angles. One angle for sp3 hybridization, ideally. One angle for reality, bond pair angle, angle between bonds. And one angle is there. It is for which orbitals? The individual orbitals which are interacting, this 90 degree angle. Originally, basically, P orbitals are separated by 90 degree, but they are moved to 107 degree. If sp3 hybridization, then it should be 109 degree 28 minutes. I want to know the answer from you. Ideally, 109 degree 28 minutes, but practically it is 107 degree. So what is happening? We are coming towards this angle, or we are going away from 90 degree. While moving from 109 degree 28 minutes to 107 degree, we are approaching to 90 degree, or we are away from 90 degree. If question is not clear, ask to repeat.
Repeat, sir.
Okay. Ideally, we expect for sp3 hybridization, bond angle as 109 degree 28 minutes. The orbitals from whom this sp3 hybridization is obtained, which orbitals are there? P orbitals. Angle between P orbitals is 90 degree. Means freely they can arrange. From 90 degree, we have to come to 107 degree for sp3 hybridization. But reality is bond angle is 107 degree. My question is, while coming from ideal state to real state, we are approaching towards this angle, or we are away from the angle between the P orbitals. Means my question is, while moving from 109 degree 28 minutes to 90 degree, during that journey, during that travel, whether this 107 degree comes or it is to the different side. Is my question clear?
Yes, sir.
I am waiting for answer. I could not hear the answer.
Repeat, sir, repeat.
109 degree 20 minutes ideal angle. 90 degree is the original situation. 107 degree is a reality situation in the molecule. My question is, while moving from 109 degree to 90 degree, this 107 degree comes or is to different direction? I repeat the question. See, if question is clear, no, then you have to answer. If you are not answering, means question not clear. There remains a number system. We consider number 0 here. We consider number 1 here. 2 here, minus 1, minus 2. What I can say, while moving from minus 2 to plus 2, this number minus 1 comes. If somebody asks me, what about minus 3? I will say it is opposite to the direction of minus 2 to 2. Likewise, in number system, there is a one number. Which number? 109 degree 28 minutes. Before that, there is a one number. That's a 107 degree. Before that, there is a one number. That's a 90 degree. So while moving from 109 degree 28 minutes to 90 degree, is that number 107 degree comes or not? That's my question.
Different direction.
Okay, different direction. Any other answer? Yes, students, are you following my question? If I would repeat, I'll repeat again, but ask me. No, unless and until you give answer, I can't move, because I want to know whether you are attending or not, whether you are understanding or not. If simple logic, if I ask and if you are not applying, then it's in vain. At least you should reply. If not clear, then I will answer. I will ask the question again. No, I could not hear. Somebody might be trying to reply, but I could not hear that reply clearly.
Sir, same direction.
Same direction.
Waiting for further two replies.
Same direction.
Same direction.
Yes, simple question it was. While moving from 109 degree to 90 degree, here see, here you will find 109 degree to 90 degree. Oh, sorry. 190 degree, this 107 degree comes, means sp3 orbital, say these orbitals are there where hydrogen bonding is there, first orbital, second orbital and third orbital. These orbitals are more inclined towards p, more inclined, more p character, more p character, more p character, and this orbital where lone pair is there should be with S character as more character. So characters present in those orbitals are different, and because of that bond angle varies. It is an additional logic we are getting for the explanation of the bond angle. So what I am saying, out of the four, this orbital first, this orbital second and this orbital third, they have more p character. Therefore, they are moving more towards the p character, p region. So bond angle is towards 90 degree. So bond angle is 107 degree. This little extra p character is there. In case of S, little extra S character is there. This in case of this orbital where lone pair is present. So how much extra S character or p character is there, that also we can find out. But for that, let me discuss one more example. After ammonia, I wrote the water as a molecule. In case of the water molecule, oxygen undergoes again sp3 hybridization, and that sp3 hybrid orbitals is the first orbital. If I consider it the second orbital, third and fourth. These two orbitals are with lone pairs and other two orbitals are with unpaired electron. It is of whom? Those are of oxygen. Just calculate this number of electrons. 2 plus 2 plus 1 plus 1. You will find 6. So 6 electrons are the outermost orbitals of the oxygen. Out of that, these 2 electrons are the unpaired electron. And it will overlap with the orbital of the hydrogen. It will overlap with orbital of the hydrogen. And I represent electron from the hydrogen in this way. So electron will pair here. Electron will pair here. So in other way, if I have to represent the structure, oxygen will be at center and oxygen will be with 2 lone pairs and 2 bond pairs. Hydrogen, hydrogen. So I can say it is the bond pair. It is also the bond pair. Bond pair means pair of electrons which are involved in the bonding. And I could label this as a lone pair. This as a lone pair. So 2 lone pairs are there and 2 bond pairs are there. As per our general consideration, this lone pair and bond pair repulsion will be there. This lone pair and bond pair repulsion will be there. And in addition to that, this lone pair and lone pair also repulsion will be there. It is the largest repulsion. Comparatively, it is a less repulsion, but repulsion is there. And because of this repulsion, the bond angle in this hydrogen, these two bonds, is considerably less than 109 degree 20 minutes, and it is a 104 degree and 28 minutes approximately. What has happened in case of ammonia? In case of ammonia, angle was 107 degree, and I was saying that this angle is less than 109 degree 28 minutes. In case of water, what happened? That angle is decreased further, and it came to 105 degree 104 degree 28 minutes. So in case of ammonia, we concluded that we are approaching towards the 90 degree. We are further approaching towards the 90 degree, means whatever the orbitals are there where this angle is measured. Answer for my question. What I said, when 107 degrees there, which is towards 90 degree, it means the orbitals where this bond angle is measured, that those orbitals will be with more peak character. That was my conclusion. Now my question to you is, here in case of this water molecule where the bond angle is there, or angle between the bond pair is there, it is towards 90 degree. So which character will be more? P character will be more, or S character will be more?
P character.
Absolutely. Here is more P character compared to this P character. But certainly your answer is right. P character will be more. Where will the more P character? Here in bonded pairs, more P character will be there. Here in bonded pairs, sorry, here I would represent, no? It's a more, it happened, it remains less. In bonded pairs, there will be the more P character. In your bonded pairs also more P character will be there. While in lone pairs, here will be S character more. Here S character will be more. And because of more P character, this angle is deviating more towards natural p orbital angle. That's a 90 degree. Therefore, the bond angle in water molecule we consider as 104 degree 28 minutes. Previously, what explanation was given? Lone pair repulsion, lot of is there. Lone pair bond pair repulsion is there, and because of that repulsion, the bond shrinks and the bond angle comes to 104 degree 28 minutes. Students, today I am giving you a new insight about the bond angle. Bond angle depends upon the character of that hybrid orbital. Bond angle depends upon the percentage of S or P character. More the P character is, bond angle will move towards 90 degree. Means if I consider sp3 hybrid orbital, and if more P character, then angle will be lesser than the 109 degree 20 minutes and will be towards the 90 degree. It is the understanding of the water molecule. Yes, students, are you finding the clarity?
Yes, sir.
Yes, sir.
Yes, sir.
Yes.
Yes, sir.
Yes, sir.
Okay. Now let me understand this bond pair. Oxygen hydrogen bond pair. Oxygen hydrogen bond pair. Yes. Help me. What's the bond angle? What is the bond angle?
104.
Yes, 104 degree 28 minutes. Our timing you can consider generally simply as a 104. The formula I give it to you. It's a very important one. Cos, the angle that we are measuring between say bond pair, say cos theta is equal to the P character minus 100 divided by P. If I have to find the S character, then it is S divided by S minus 100, or you can say the 100 minus S. The modulus you can what consider. This is a formula for the determination of P character. Now at this moment, what we know this theta. Just now one student has answered. Theta is equal to 104 degree 28 minutes. Now let me substitute. Cos 104 degree 28 minutes is equal to, let me write only the one. Yes. Can anybody answer what is cos 104 degree 28 minutes? What's the answer? Yes, I think you'll use the calculator. No, you can work on that. What is cos 104 degree 28 minutes? Yes, student, could you see the calculator which I am showing here?
Yes, sir.
Okay, the angle is 104. And I want the cos function, cos angle. What is the angle? Minus 0.24. This is about almost what the 0.25. Actually, 104 degree 28 minutes is there, no? Okay. Otherwise, what I consider simply 104.5 and its trigonometric cos function. What is the answer? Minus 0.25. Could you able to see the screen of calculator?
Yes, sir.
Yes. So what is the answer? Here is a minus 0.25, which is equal to P character minus 100 divided by P. If I have to simplify, let me bring this P to the left side. So what I will get now? Minus 0.25 P character is equal to P character minus 100. Students, could you able to understand what I'm saying?
Yes, sir.
Yes, sir.
Yes. If I simplify it further, then let me bring this P to the left side. Minus 0.25 P plus P. Means I would write minus 0.25 P plus P. Just I am bringing P to the one side is equal to minus 100. So this minus and minus, I cancel that. So what's the answer? 0.25 P. Sorry, just wait. Sorry, I'm wrong there. I can't cancel that. First, I need to do this addition. Minus 0.25 P plus P. What's the answer? Am I correct or wrong? Yes, are you following the step? What I said? See, here, one mistake was there. I am correcting now. Now pay attention. But before that, I want to know reply from you. Are you following?
Yes, sir.
Yes, sir.
Okay, what I do now, I bring this P to left side. Simply, help me now. Minus 0.25 P. What shall I write here? Minus or plus? This P I am bringing to left side. What shall I write here? Here it was with the plus sign. Yes,
Minus.
it will be minus P, which was wrong previously. Oh yes, right. Is equal to this term as it is minus 100. Let us simplify this. Minus 0.25 P minus P. What's the answer? I am asking you to solve this portion. What's the answer? No, I can't help you, student. If you could not answer this sum simple, then you are not using your brain. Means you are not giving
Minus
a single
1.25 P.
Right. I want further 5 answers.
Yes.
Question is very simple. Minus 0.25 minus 1. That's the question. And if you could not.
Minus 0.24.
Okay. Further 3 answers I want.
Minus 1.25 P.
Saurabh did typing now. I want answers. Now I want from everybody the answer. Shubham, have you answered?
Yes, sir.
Gaurav?
Yes, sir.
Mandar? Okay.
Yes, sir.
Now you are answering. That I want. No, you have to talk loudly. Now I came on the screen of the Google presentation and therefore I come to know you are giving answer in the chat box. I said when I'm giving presentation, at that time you have to talk. Yes. I write your answer minus 1.25 P, which is equal to minus 100. What I do now, minus sign are both side. I cancel those signs. Are you understanding what I'm saying?
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
Yes. Therefore, P is equal to 100 divided by 1.25. Yes. What is the answer of that? 100 divided by 1.25.
80.
80.
Yes, it is 80%. 80% of P character. We were expecting 75%. But see here, character is 80% means P character is increased, P character is improved. If P character is improved, then accordingly S character will be less. I ask a simple question to you. If P character is 80%, then how much S character will be there? If
20.
P character is 80%, yes, S character will be 20%, which is not 25%, which is not 25%, means S character is decrease and P character is increase. That's a speciality of bonding orbital. That's a speciality of bond pair. Means when I consider oxygen and hydrogen is bonds, when we consider this bond pair has more and more P character, and therefore this bond angle is towards the 90 degree. And where the lone pairs are there, that those lone pair situation, those orbitals, of course those are sp3 orbitals, but in the sp3 orbital, more which character is there? More S character will be there. Here more P character by how much percent? 5% extra. 80% P character and 20% S character. But if I talk about this lone pair, S character will be, yes, S character will be, help me, in case of lone pair. About bond pair we need discussion. Okay, you work on that. You can consider the angle between the lone pairs, and with that also you can solve, or other way equal number of orbitals are there, so how much decrease there, that much increase will be there. So S character and P character that you can find in the lone pair. But certainly there will be more S character than expected, that's so 25%. So percentage of S and P character that we have discussed. further few things are there. I'll cover those things in the next lecture, and that lecture will be the last lecture for our theory syllabus from my point of view. But if wherever you have question, doubts are there, we will discuss. So students, what is the assignment today? What we have discussed? The first point of assignment is bond angle in ammonia molecule, in water molecule. Second, reason for the deviation in the bond angle. Third point, S character and P character. Fourth point, calculation of S character and the P character. Similarly, you can perform the calculation for ammonia. So calculation for water molecule, bond pair, angle, and S and P character I told to you. For ammonia molecule, you have to work. What will you do? Here, I consider the bond angle as 104 degree 28 minutes. For ammonia molecule, which angle will you consider?
107.
Exactly. Scientific calculators are readily available. So with that, you can calculate. Means not necessary to purchase. Online are available, and you have to find the P character. If you find P character, S character, you can find. So what the workout I did for the water molecule, same workout you have to do for the ammonia, and that's the assignment. That's a summary of today's lecture. Is the task clear?
Yes, sir.
Yes, sir.
Okay, already I stopped the presentation. Okay, fine. So shall we stop now? Okay, students, then I stop the recording and I declare here today's session is over. Quit now.